I don't wanna grow up, I'm a curious kid. The world has 100 questions I can play with. So I'll open my arms and eyes and wonder every day till the day I die. No one really knows why gravity exists.
Welcome to Wonderfest, the Bay Area beacon of science here at HopMonk Tavern. Thank you for being here. Huzzah! I am so glad. This is the last in the series called Ask a Science Envoy, the last for 2025. There'll be a new series starting probably in March of next year, 2026. Our first speaker, Ashley Moses, is a researcher and PhD candidate in neuroscience at Stanford University. Ashley earned her undergrad degree at the State University, at Florida State University, double majoring in biology and psychology. At Stanford, she works to understand human behavior, particularly focusing on the brain's neurotransmitters. Ashley loves science communication, and in fact, she runs her own science outreach nonprofit, competing with Wonderfest, I guess, in a way. Her own science outreach nonprofit called The Civilian. Maybe she'll tell us a little about that tonight. But here to talk to us about neuroscience is Wonderfest Science Envoy, Ashley Moses.
Okay, so thank you so much for having me. I'm really excited to talk to you today about the brain and neuroscience and behavior and all the things that Tucker mentioned. But we're going to do it hopefully in a cool way, a little bit of a fun twist to thinking about the brain and thinking about behavior. So during my PhD, I have felt more and more like a detective each and every day. And I thought it would be fun to give you all sort of that experience, that emotion. You could feel it with me because I'm still feeling this literally earlier this morning. So we're going to just kind of hop into it and hop into the case. If at any point you have any questions, feel free to interrupt me. But I know we also have time at the end where we can chat more specifically. Okay. All right, so before we open the case, let me introduce you to the main players in any good brain mystery. It's the neurotransmitters. These are chemical messengers, tiny molecules that travel between brain cells and tell your brain what to do. They influence everything from how you move to how you feel. A thought, a mood, a reflex. Neurotransmitters make it happen in milliseconds. So we need to move quickly, and we need to figure out the culprit here. So most brain functions involve a network of transmitters working together or getting in each other's way. And so an important note for you detectives is that they don't always work alone. They might actually be working together. All right, so again, a little bit of background information. I'm going to introduce us to an analogy here just to really hone in on the neurotransmitters. So think of your brain as a city. Think of the neurons or the brain cells like the buildings within the city, and the neurotransmitters or the potential suspects here are the texts and the calls happening within the buildings, right? So if there's a building on fire, you would want to know that. If there's yummy food at a truck down the street, you would also want to know that. And so the communication throughout the city lets you know what's happening, good and bad. The same goes for neurotransmitters. If you're hungry, sad, happy, or mad, neurotransmitters are involved. They're sharing that information throughout the brain to prep you for a response both physically and mentally. And so we love when they do their job. We love when they tell us something is positive or they protect us from something that is negative. They can communicate when we like something or when we don't like something. But when these systems go awry, they cause disarray. And as you can imagine, when the city's communication channels shut down or even intensify, then the city doesn't function the same way. Same goes for our neurotransmitters. When they function abnormally, this can lead to issues in our brain, causing psychiatric disorders such as anxiety, depression, Parkinson's, or schizophrenia. And so, welcome, detective. Today we are going to hop into a case of one of those psychiatric disorders, specifically depression. Our subject is unfortunately dealing with things that are negatively impacting their way of life. But we don't know what's going on in the brain, and I could use your help. The subject has lost motivation. They're no longer experiencing reward in the same way that they once did. They're not engaging with their environment, and they're feeling a lack of drive or focus. And we think this has to do with neurotransmitter functioning. I will present 3 clues of symptoms, and we will go through 3 suspects. And then at the end, I want all of you to tell me who it is. And we will vote, and we will see who is correct. So please pay attention to these clues. So our task, like I said, is to examine the suspects and reveal the truth behind this missing motivation. Okay, so clue number 1. Our subject has lost interest in things they used to love. There's no interest in reward. There's no desire to pursue things that are rewarding. They don't want to socialize, and they've expressed indifference. These are classic features of mental health disorders like depression. The inability to experience pleasure or enjoyment is known as anhedonia. Clue number 2. Our subject is alert, but they're not intrigued by anything. But they're not sleepy. They're awake. Their sleep systems are not bothered by this. But they're not engaging with things around them. They can't focus, and they seem distant. So again, we think we've nailed it down to this depressive-like behavior, but we don't know what's going on in the brain. Clue number 3, the last one. The subject can move, but they don't choose to. So we know that physical functioning is intact, they're just inactive. They want to stay in bed, but there's no signs of muscle weakness. So this is clearly something of mood and affective disorder. And so from these clues, we think there's something going awry in the communication signaling within the brain, leading to this depressive-like state. And this has led us to the brain's communicators, the neurotransmitters, or as their group is called, the transmitters. We think dysfunction is one of their pathways. Dysfunction in one of their pathways is the reason for this effect. But like I said, we don't know which one is responsible. So let me introduce you to the suspects in hopefully a goofy and fun way. These are our suspects. We've got dopamine, serotonin, and histamine. These are 3 neurotransmitters known to function very widely in the brain. And before we get more deep into each one of their functions, we're going to hop back to our city analogy. And if we think back to this analogy, it gives us important insight into the brain. Each of these transmitters, dopamine in green, serotonin in purple, and histamine in blue, each of these transmitters comes from certain locations, like neighborhoods in the city, but spread throughout to regulate what's going on. So dopamine originates from a neighborhood or a brain region called the ventral tegmental area and spreads throughout the entire brain, or the whole city. Serotonin originates from a neighborhood known as the dorsal raphe, and again spreads throughout the entire city. And histamine originates from a neighborhood known as the tuberomammillary nucleus, and again spreads throughout the entire city, causing havoc and sometimes causing good things everywhere that it goes. And so those names of the neighborhoods are not important. But what I'm trying to hone in on here is that they go everywhere. And this is the area where we think the crime has occurred. We think the symptoms that are arising are coming from this neighborhood, a neighborhood known as the nucleus accumbens, a key station for motivation and processing in the brain. But as you can see by the squiggles on the screen, dopamine, serotonin, and histamine have all been there, and they continue to travel in and around that neighborhood. So now, as the story gets more and more complicated, let's look at the suspects. Dopamine, also known as the hype man. Dopamine is the guy you think of when you experience pleasure. So when you eat the pizza on the table in front of you, when you eat the cookie back home and you love it so much and you need another one, that is dopamine. So please think fondly of dopamine when you can. Unless you don't want the cookie, then be mad at dopamine. However, dopamine's therapeutic role is a bit more nuanced, and we need to consider that when we consider our subject. Dopamine targeting drugs have been used to treat things like Parkinson's, ADHD, and schizophrenia, but its role in depression is still unknown. So while we think our subject has a depressive-like nature, we don't know if it's dopamine, even though dopamine is the one involved in reward, movement, motivation, and mania, things that have been involved with our subject. So dopamine is always in the spotlight, but is dopamine guilty this time? Okay, so next we have serotonin, affectionately known as the balancer. On a day-to-day basis, when you feel calm after taking a walk in sunlight, think of serotonin. That's pretty much what's happening in your brain. So serotonin has been known to play a role in regulation of mood and emotion, in learning and memory, sleep, and appetite, leading us to think that based on the clues we know from our subject, serotonin might be involved. Fun fact, today the most commonly prescribed drugs for mental disorders such as depression is Zoloft, a drug that increases serotonin levels in the brain. This led us to think serotonin might be the one causing the symptoms we're seeing. However, even though these drugs are very popular, they aren't perfect. And targeting these drugs only has about a 40 to 60% success rate. And so it could be serotonin, but something more might be going on here. And so serotonin is known as the happy hormone, but you cannot underestimate the nice types in this scenario. And our last subject is histamine, also known as the insider. Histamine plays a role in arousal and sleep, allergies, motivation, and cognition and memory. You're probably all quite familiar with histamine targeting drugs, actually. Think of antihistamines like Benadryl, Allegra, Claritin, or Zyrtec. That's your guy. Histamine's your guy. So think of histamine when you sneeze and because of the flowers, okay? So blocking the effects of histamine in the brain is specifically for allergies. So you might be wondering, Ashley, you're a terrible detective. We're talking about depression here. Why are you bringing me a neurotransmitter that has to do with allergies? I get it. But recently, histamine targeting drugs have started to be used to treat mental disorders like anxiety. So what once was thought to just be for allergies now has this new therapeutic potential that makes people more interested in this molecule. So we had to consider it. Hopping back to neuroscience for a second. Around the time neurotransmitters were being discovered in the 1960s, there was actually a technical issue that made histamine harder to detect. So serotonin and dopamine went on to fame, and histamine was left in the dust. And so this is another reason why our team has brought histamine to the forefront. Just because histamine has remained under the radar for decades doesn't mean it's not involved in the clues that we're seeing. So something doesn't add up. All right, so I'm going to bring it back to the clues. What we know. Our subject has lost interest in the things they used to love. No pursuit of reward. They are alert, but they're not intrigued by anything. So their sleep systems are not impacted. And finally, they can move, but they choose not to. So physical functioning is intact. So I ask you all, detectives on this case, who do you think did it? Can I see a raise of hands for dopamine? Okay, good. We have maybe 5. Serotonin. And histamine. Nice. Just a quick sneak peek. First of all, thank you all for playing. I appreciate it. Secondly, for those of you who are very excited about histamine, I'm going to need to take you with me, and you can tell my advisor how excited histamine is. So that's great. I'll save that for another time. Okay, so now, before I reveal the answer, I have to confess something. What I'm about to say is one of the most important phrases in science. It's also the hardest phrase, one of the hardest phrases to say, and it causes the most frustration and the most political strife. And please don't get mad at me, because I hope you didn't come here for answers, but we don't know. We have no idea, absolutely no idea. I'll just leave now. Okay. So we have a lot of clues, and we've ruled things in and out tonight. But motivation, depression, these psychiatric disorders are complex, and the brain doesn't give up its secrets easily. The truth is, it's not just dopamine, and it's not just serotonin, and increasingly, we think histamine might play a role, but the case is still open. And so we're going to go back to the city real quick. We can see these neurotransmitters moving all around, keeping everything running smoothly. Thank you to neurotransmitters. And the same goes for the brain. So this is my PhD currently. This is my job. I need to figure out how these neurotransmitters are interacting with one another in the brain to lead to these disease states. This is what science often looks like. Clues, dead ends, surprising suspects, and sometimes no answers. But that doesn't mean we're failing. It means the mystery is deeper than we thought, and that's what makes the chase worth it. So I'm chasing histamine down right now, while others in my laboratory are chasing down dopamine and serotonin, and we will see who the culprit ends up being. But I have a sneaky suspicion that it's probably all of them. Thank you.
Question. Are all antihistamines anticholinergic? Or some?
Ashley, let me ask. You were plenty loud, sir, but I'll Ashley to repeat your question. If it's too hard a question, she will change it to make it easier.
Okay. He asked, what do I like about science? No, I'm just kidding. You said, are all antihistamines anticholinergic? That's a great question. So,
You probably should explain what that means.
Yeah, I don't know.
sure. So, it's a great question. So, histamine, we've talked about today. Antihistamine is blocking histamine in the brain. Cholinergic has to do with acetylcholine, which is another neurotransmitter that I did not talk about today. It's very prevalent in some of these same pathways in the brain that have to do with reward and motivation processing. So anticholinergic, anti-acetylcholine in the brain, blocking acetylcholine in the brain. So that is a really good question. In fact, I don't have an answer, which is probably what's going to be the theme for tonight. But some research suggests that histamine actually decreases dopamine activity through these acetylcholine neurons. And so what I'm proposing, actually I proposed it today to my thesis advisor, is that acetylcholine is sort of the middleman between histamine and its impact in some of those reward processes. And so do I know what antihistamines are doing to acetylcholine functioning in the brain? No idea, but I hope in 3 years I'll have a better answer. Thank you.
Can I pursue that a bit?
Sure.
So my understanding is that older antihistamines like Benadryl do have a very intense anticholinergic effect. And if you take them chronically, you start to inhibit acetylcholine production in the brain, and the result is dementia because you don't have the appropriate amount of neurotransmitter. Is that a reasonable notion or hypothesis?
So for folks who are familiar with Benadryl, there have been certain claims where if you take Benadryl for a very long amount of time, it can lead to dementia due to disruptions in acetylcholine circuitry and processing in the brain. I have heard the same thing. We know that acetylcholine plays a large role in cognitive processes in the brain, and so it makes sense if you disrupt that for a very long amount of time. I think a lot about night shift workers, actually, who are known to take Benadryl to help them sleep during the day. And it's actually been reported in these populations that that's a no-no, and it can lead to some issues. So any long-term disruption to your neurotransmitters or the communicators within your city is going to lead to disrupted communication. Absolutely. Great question. Thank you so much. Yes.
Electroshock, depression, how does that work?
I don't know. Oh, how are they using electric shock to cure depression? Yeah, this is actually not in my area of expertise at all, so I'm hesitant to speak too much. But I know that there have been plenty of groups, specifically at Stanford, that use magnetic stimulation within certain parts of the brain, whether it's on the outside or even sometimes deeper, to lead to sort of altered signaling wavelengths within the brain that might cause a alleviation of some of these symptoms. So it's definitely an avenue that scientists are pursuing. It's one that I know very little about. I apologize. Yes.
Or Charlie, or that one is so glad when the electroshocks are over, a natural state of joy sets in. Yes.
Absolutely. One avenue, actually, if I might add on alleviating symptoms that my lab and others are exploring are in psychedelics. So that's a cool space that I think is increasing attention recently. So I keep a lookout for that. Yes.
What are you using as your test subjects? Are you doing animal studies, or are you continuous human studies?
Sure. So the question was, what model organism? What am I using to test these theories and these ideas that I have? I use a mouse, and with really cool new technology, we're able to record neurotransmitter activity in the brain. This is something called fiber photometry. So I can literally give a mouse a Fruit Loop and watch dopamine go up. It's pretty darn cool. Same time, it's really cool. And for anybody who's interested, I can also watch histamine go down at the same time. So we're seeing these opposing effects. And if you haven't noticed already, I'm very biased towards histamine. So I think there's something cool going on. There's also a technique that we use where you can genetically manipulate the mouse's brain and stimulate it with light to stimulate certain neurons in the brain and lead to behavior called optogenetics. So light and genetics, excuse me. And with that technique, I'm able to sort of control behavior. I can send light into the mouse's brain and hopefully see something happen. So something cool that I've seen in my own work is when you stimulate the mouse's histamine neurons in the region with dopamine, you get increased social behavior, which is something we might not expect at all. So there's a lot of complicated things happening, and I just keep saying I have no idea. I don't know, but it's a mouse, yeah. Yes.
What about GABA? Like, there's some theories that GABA is also, why study GABA versus histamine, or it seems like it's on the frontier.
Sure. So why not study another neurotransmitter called GABA? So it's actually funny that you say that. The other day, some data presented itself to me that said that I should probably look at GABA. So thank you for that. Essentially, I started studying histamine because I felt it was so overlooked. There are these people prescribing histamine targeting drugs to treat anxiety, yet we have no idea what it's doing other than allergies or sleep. There have been other studies that have shown its role in cognition and memory. And I wanted to take a little bit of an entrepreneurial approach to my PhD. Let me try something. Everyone keeps talking about dopamine. Let me study histamine. And so a lot of people also talk about GABA. And so I tended to go towards sort of the underdog here, but I think GABA is more and more on my radar as time goes on. Yes. Purple long sleeve? Yes.
Yeah. I know that cognitive therapy is recommended for depression. Have you done any studies on how cognitive therapy can affect neurotransmitters?
I personally have not. So have I done cognitive therapy? Has been known to help with symptoms of depression. Have I done any work looking at cognitive therapy and its role on neurotransmitters? Okay, good. I have not. So my research takes a very basic approach. I focus a lot on mouse neurocircuitry and the ways in which these neurotransmitters are functioning in the first place. I have not translated it beyond that to sort of these symptomologies and sort of disorders. And so we have work in the lab looking at things like autism and frustration and aggression and all these other translatable topics. Right now I'm focusing on the histaminergic circuitry, and then hopefully from there I can move forward to things like addiction and motivation and depression. So I have not personally, but I'm sure somebody has. More questions? Okay. Yes.
Is there a part of the brain that you're focusing on?
Yes, there is. Okay, is there a part of the brain that I'm focusing on? So I showed you this city map a little while ago, and I told you green was dopamine, purple was serotonin, and blue was histamine. So I'm really interested in, can you see my cursor? Great. I'm really interested in this connection right here. So histamine neurons originate from a very tiny region in the brain called the TMN. They project to the VTA, which is where dopamine neurons in the brain originate. In fact, the VTA is one of the topmost regions that receives the densest projection from histamine neurons. And anybody in here who's following how much I am excited about histamine can see that this is exciting, right? The VTA, where all the dopamine neurons are, or at least a majority, receives massive projections of histamine neurons. Why are we not looking at that? And so I am interested in the connection between that blue circle in the bottom right and the green circle on the bottom left.
Is Tylenol, does it fit into any of those three categories? And I'll tell you why. You want to know?
Sure, please.
Oh, okay. I was listening to Science Friday one day, and they were talking to someone, and it was about depression. And they said they found that people who were depressed, like maybe they split up with a partner or something that bad had happened, Tylenol helped them. And I had never heard that before, and somehow it stuck with me, and I've never repeated it until now. But
Sure. So for folks who couldn't hear, Tylenol as a potential cure for a bad breakup, essentially.
depression.
So maybe Tylenol being a way in which folks can sort of deal with the symptoms of depression. I have actually never heard of that before.
Yeah.
I have never heard of that before. But like we were talking about with Benadryl, right? If you're coming in there and you're messing with these communication systems within the brain, no matter which one they are, they're all connected, and I could see something like that maybe happening. We do need to consider maybe a placebo effect. Maybe somebody's taking some sort of drug, and then at the end of the day they say that they feel better, but I'm glad they were able to get over the breakup. But I'm not sure. I'll have to look into that. Yes.
Is there any implications in your research for whether people who are depressed shouldn't be taking a lot of antihistamines?
Okay, so people who are depressed, should they be taking antihistamines in order to...
allergies.
If they have allergies. Oh, I will not make a claim on that one. That one's pretty tough. But I know, so the professor that I work for in the laboratory, one reason why he's actually interested in histamine alongside me is because he's a psychiatrist, and he prescribes an antihistamine for anxiety. So does his psychiatry colleague. And they were like, we have no idea what's going on. We just know that maybe it makes you a little bit sleepier, and that's why it decreases your anxiety. And so I think anxiety and depression, yes, are different things, but I really think histamine has this grand therapeutic potential. But please do not go take any drugs on my behalf. That would be the worst. Yes.
How is the dopamine release from things like TikTok affecting people's brains?
Such a good question. How is dopamine release from TikTok or other forms of social media affecting people's brains? That's such a good question, and one I think about constantly. So as I've mentioned in this talk, you eat a cookie, you get a rush of dopamine, you want more cookie. Now imagine if you see a really awesome TikTok video, and it makes you laugh, and it's quick, and you want another TikTok video, normally. And so it's very easy for the reinforcement of that behavior to stick with you, and you might even start to become addicted. I've actually heard of these places in Japan where I believe they're treating social media addictions in children because it's becoming so prevalent. And so something I would say is maybe take a break from the TikTok every once in a while, and maybe go for that serotonin rush in a calm walk outside. But indeed, dopamine plays a role in social media in children. Thank you for that question. Have you raised your hand multiple times and I missed it? Okay. Okay, great question. Blood pressure impacts the brain. I haven't even begun to talk about in this talk how many peripheral effects these neurotransmitters have. We actually know that in your gut, there's a huge amount of serotonin. What is it doing down there? Right? What's going on? And so we have folks at Stanford looking at neurotransmitters within your gut as well. And so things like blood pressure and vasodilation and vasoconstriction are partially controlled by some of these neurotransmitters, which sometimes function as hormones as well and can move through the bloodstream. And so I don't personally study that, but it is a key role of these neurotransmitters to function in homeostatic properties as well: sleep, blood flow, etc. Yes?
You mentioned the use of certain drugs, current drugs, to treat these conditions that derive from a deficiency of certain neurotransmitters. Are there known mental type or mood conditions like these that might also derive from an overproduction, too much of a neurotransmitter, as opposed to a deficiency?
Absolutely. So are you asking sort of which of these disorders might be due to too much of a neurotransmitter or too little?
Are there known disorders that can be nailed down to having too much production, either by a faulty control system or some other mechanism?
Absolutely.
Too much neurotransmitter instead
Sure.
of deficiency.
Okay, talking about this balance of neurotransmitters, too much or too little. So I've mentioned too little. Maybe we think about Parkinson's, where you have a depletion of dopamine in your brain. That's why maybe treating it and supplementing dopamine would be beneficial for many folks with Parkinson's. Now let's think about too much. This is where we get into the antihistamines. So histamine actually increases in your body when you are having an allergic reaction or sort of these inflammatory processes. And so that's why an antihistamine would be bringing that down. And so we have dopamine, maybe in some instances you'd want to bring it up due to a depletion. And then histamine maybe is too high when you have an allergic reaction. We want to bring that down. So it's really this interesting balance that your brain is doing. But what I find even more interesting is if those systems are interacting with one another, when you bring one up or you bring one down, what's going on? There have been some Parkinson studies that have actually seen an opposite reaction in histamine and dopamine, right? So if we start doing this, what are we doing up here and what are we doing here? We don't know. I actually should flash that slide again. Yes.
I've heard that magic mushrooms do well with depression. How is that related to serotonin, dopamine, and histamine? Or is it not? Is it a separate entity into itself?
Sure. So magic mushrooms, great question. Is it connected with the neurotransmitters I've talked about today, or is it a separate entity? First off, you are on the brink of grand scientific discovery. So this area of magic mushrooms, psychedelics, is just exploding right now. We need to do it carefully, because when it explodes and the public sees it explode and then they think it's safe or ready to go, it's just, the science isn't there yet. Now, some studies from collaborators with our laboratory are looking at serotonin specifically with sort of these psychedelic compounds. And so I don't know much about histamine. I'm sure dopamine is involved, sort of this rewarding state, but I've heard that these psychedelic sort of trips can actually be really wonderful for depression and anxiety, but how and why is just the biggest black box right now. So I would cautiously keep an eye out, but if you're doing anything to perturb the brain, you're doing something to these neurotransmitter systems.
Wow. One more question?
Yes.
So this is very weird and esoteric, but I understand there's a lot of major histocompatibility complex in the brain, and I don't know why, and I wonder if it's related to the histamine stuff that you're working on.
Sure, so histocompatibility and the stuff that I'm working on with histamine, I have no idea. I really don't. I hope that you all will forgive me for saying I don't know so many times. I think histamine has gained a bit more attention recently in some of the wellness culture as well, with like histamine intolerance, histamine diets, etc. And so that is a space that I have not even touched. It's actually a note on my computer that says, what is histamine intolerance? Like, I just need to sort of understand a bit more about histamine in a broader sense. But in relation to your question, I don't know. I'll try to figure it out. Thank you so much.
I don't know that well-positioned times in your qualifying exam can be a big help.
Great. I actually have a thesis committee meeting coming up in a month, so I will be using it. Thank you so much. I appreciate it. Oh, the nonprofit page? Yes, I can share that link somehow, but I run a nonprofit called The Civilian that works with scientists like the professors that I work for to help them explain their research in a way that actually makes sense. So I don't know if any of you have ever tried to read a scientific paper. I don't recommend it. It's actually pretty terrible. And if I were to hand that paper to my mom or my grandma or my brother, they would say, thank you for the coaster. You know, they wouldn't even read it. And that is years of knowledge and years of discovery just gone. And so the Civilian's goal is to work with these scientists to create a lay summary at a high school level, underneath an 11th grade level here in the US. And so I'd be happy to share the information. It is just thecivilian.co. And that is our current repository. The Civilian.
The Civilian.
.co. Civilian like a person in the town or city or no.
I have reason to believe that Ashley and her speaking partner will hang around after the presentations for you to ask further questions and get that dopamine hit that you're really all after. So Ashley, thank you again.
Great job.
Thank you. Now, let's do a little computer transfer here, and I get to introduce our second speaker. Savvas Marcou is a researcher and advanced PhD candidate at UC Berkeley. Go Bears.
Go Bears.
Savvas grew up on the island of Cyprus in the Mediterranean Sea. He ventured to England to earn a master's degree, a Master of Science degree in geophysics, with first-class honors, by the way, from Imperial College in London. Then Savvas came west, far west, to join the Berkeley Seismology lab. In total, he has traveled over 7,000 miles to live and work in, and he's choosing to do this, in earthquake country. Please welcome seismologist and Wonderfest Science Envoy, Savvas Marcou.
Thank you, Tucker, for the introduction. And that was a great talk, Ashley. So I hope I can live up to that with my talk. So as Tucker mentioned, I'm a seismologist. I spend a lot of my time looking at wiggles that recorded from earthquakes. But this talk has a twist. We're going to talk about earthquakes and smartphones at the same time. So let's give you a bit of a flavor as to the journey we're going on today. And first of all, I want to touch on questions that you really, really want answered. So I bet that every person in this room really wants to know when the next big earthquake is going to be. So feel free to ask me that question, but I'm afraid I will disappoint you, because I don't know. Your guess is as good as my guess. However, the question we will be dealing with in this talk is when the next big earthquake happens, how strong is the shaking going to be where you live or where you work? And we're going to do this in three parts. We're going to talk about what we know about earthquake shaking. We're going to talk about the big problem facing people trying to guess how strong the shaking will be in the next big earthquake. And I'm going to tell you a little bit about how I think there's a promising solution in your backpacks, in your pockets. So, let's get into it. Stating the obvious here, but earthquakes can shake the ground pretty hard. So I'm pretty sure most of the people in this room have felt an earthquake before. But just to confirm my suspicion, let's go hands up. Who's felt an earthquake before? There we go. No surprises here. We live in California, earthquake country. California gets a lot of earthquakes. So here's a collection, a collage from down the years, starting with 1906, the big one in San Francisco, going all the way to last December up north in Cape Mendocino. California gets a lot of earthquakes. So what do earthquakes do? Earthquakes cause the ground to shake. And that shaking causes things to fall, break, and collapse. And contrary to what people think, it is not the shaking that makes things break. It is falling things and breaking things and collapsing things that damage your property, that injure people, and can ultimately kill. So let's go much closer to home. Let's come to the Bay Area. And I want you to cast your minds back to 1989, the Loma Prieta earthquake, an earthquake that really shook the Bay Area to its core. This was known, I think, as the World Series earthquake. There was a baseball game going on during this earthquake, the afternoon of October 17, 1989. The earthquake started in the Santa Cruz Mountains. It caused quite strong shaking across the bay, but what people will most remember is that the Bay Bridge collapsed. There was strong shaking that made the east span of the Bay Bridge collapse. The damage across the bay was $14 billion in today's money. That is a lot of money. That is more than what my small country produces in a year. So it is a lot of earthquake damage. In San Francisco, the Marina district experienced a lot of damage. So earthquake shaking matters. And in the Bay Area, we have an earthquake problem. But fear not, there are solutions to this earthquake problem. Number one, earthquake early warning. Number two, we can make our buildings strong to withstand the shaking. So we'll spend a little bit of time going into these two solutions here, starting with earthquake early warning. So who's heard of earthquake early warning before? A few people, that's good. So earthquake early warning is nothing but a system that we have here on the US West Coast that can give you a few seconds of warning before the shaking gets to you. It is a shaking spoiler, if you like. Now this system that we have on the US West Coast is really a triumph of science. $34 million of your tax money every year go into developing this system. It is now live. It has been live since 2019. It has sent alerts to real people like you 150 times for 150 earthquakes. And it is predicted to be able to save us about 10 to 20% of the damage in the next big earthquake. So earthquake early warning gives me a nice pass to introduce the star of today's show, that is MyShake. So MyShake is a smartphone app that is freely available for you to download on your smartphone. And just out of curiosity, has anyone downloaded here? So a few great fans of MyShake, go MyShake. But for those of you who haven't heard of it before, it is an earthquake app that principally takes the messages from our shake alert system, the early warning system, and delivers it to people. However, MyShake was not conceived to do that in the first place. It is the birth child of a brilliant PhD student at UC Berkeley 10 years ago who thought that smartphones can collect earthquake information. And right now, his dream is coming true because 1 in 20 people in California have MyShake on their smartphone. And that number is growing. We just broke 4 million downloads, making the state of California, who funds us, extremely proud for its investment. However, MyShake collects earthquake data, as I have mentioned already. And the star of this data collection is smartphone waveforms. You guessed it, wiggles. I'm a seismologist. I like to look at wiggles. So how do we do that? In your smartphone, you have something called an accelerometer. It is the device that can tell if your smartphone is upright or if it's tilted. It's the annoying device that makes your phone like flip its screen back and forth. But it is an accelerometer. It is a device that can record vibrations, waves, when they hit your phone. So we can record ground shaking and earthquakes this way. So let me take you on a bit of a journey to discovering how strong we need our buildings to be built. How strong can the next earthquake shake? And we're going to go on a bit of an exploration to see what we know about what determines how strong an earthquake shakes. And I can't talk about earthquake shaking without talking about earthquake magnitude. This is a single number It's the number you hear about on the news. There was a magnitude 5 earthquake, a magnitude 6 earthquake. So this is nothing but the size of an earthquake. It is how much energy the earthquake puts into the ground and how much energy it is available to shake you. So it goes without saying that bigger earthquakes tend to shake more, and they tend to shake bigger areas as strongly. But a thing that not many people know about magnitude is that magnitude is logarithmic, a big scientific word, which means that you go up 1 unit on the scale, you will increase the amount of energy many, many times. For magnitude, 1 unit increase means 32 times more energy. And I cannot illustrate this better as a Mediterranean using pasta. So we have a magnitude 5 earthquake here. It is 1 piece of spaghetti. Go to a magnitude 6, we have 32 pieces of spaghetti. A magnitude 7, which is only 2 units up from about 1 spaghetti, magnitude 5 earthquake, is 1,024 times more energetic. Has 1,024 times more energy than the magnitude 5. So keep this in mind. Magnitudes, we know pretty well. Bigger magnitudes shake more. That's a good start. However, as with anything that the Earth produces, the story is not that simple. Each earthquake has 1 magnitude, but it has many intensities. So as we've already mentioned, magnitude is the size of the earthquake. Each earthquake has 1 size, but it has many intensities. Intensity is the local description of ground shaking. So I will use the example of the Loma Prieta earthquake once again to illustrate this. This is a map that has lots of splotches of color, and this really describes the strength of ground shaking on that day in 1989. The intensity of shaking is described on a 10-point scale, shown here quite annoyingly in the Roman numerals, from not felt all the way up to extreme. Redder colors indicate stronger shaking. So let's establish some ground rules for earthquake intensity. Number 1, intensity decreases with distance away from the earthquake. That makes sense. I go far away from that light bulb, I would perceive that light bulb to be less bright. But if this was the end of the story, this map would not look like an abstract painter's product. It would look very symmetrical. Going around the earthquake, the colors would go from red to blue very predictably. So there is a spanner in the works in that the stuff that you sit on matters to how strong the shaking will be. So it turns out that if you're on hard rock, you will tend to feel much weaker shaking than if you are on soft rock. Kind of makes sense. Soft rock is like a ball of jello. It will tend to shake a little bit more. But we don't guess as seismologists. We like to have hard truths. So I give you my microphone, the seismometer. So the seismometer is a tailor-made instrument that is made to pick up ground vibrations. So when you put it into the ground, it looks a little bit like an inverted pressure cooker. So this is the seismometer with all its casing. We make sure that it's all packaged nicely because it's a very sensitive instrument. It picks up all sorts of vibrations from trucks, me walking next to it, people stomping their feet. It also picks up ground shaking. But another thing you need to know about a seismometer is that it is very, very expensive to deploy. Each one of these units costs tens of thousands of dollars. So I would love to have one of these every couple of feet, but we don't have the money to pay for that. However, where we have been able to put seismometers, we have discovered a treasure trove of new knowledge. And the number one thing that fascinates me every single time is that earthquake intensity varies a lot in space. So let me illustrate this with an example from 1989. Once again, who remembers the Cypress structure collapse in Oakland? Big surprise for the city of Oakland. Their big raised freeway collapsed. And we can explain this using the very facts that I just presented right now. So in this map in the middle, we have 3 colors. We have these beige colors that represent sand. We have these brown colors that represent rock. And we have these gray colors that represent mud. And in this panel here, we have wiggles from each of these three rock types. Top, bedrock, small vibration, not a lot of vibration going on. The bottom, sand and gravel, a little bit more vibration on the rock. But then in the mud, a lot of vibration is going on. And incidentally, yes, you've guessed it, where was the hyperstructure that collapsed? In the mud. So this is, again, this is amazing. We have 3 records within 3 miles of each other, and yet they could not be more different. So I've shown you the Bay Area story. Let's go down to SoCal, Los Angeles. 1994, the Northridge earthquake happened in LA. And this map, it shows you, is a pretty old map. This map is older than me. This paper got published in 1997. And this is an experiment that people ran in LA where they deployed a bunch of seismometers and they tried to see at each of these locations that they deployed their seismometers, these circles in this map, how much was the location amplifying, making bigger, or de-amplifying, making smaller, the ground shaking, on average, with respect to a reference point. So this map, you will notice, it's pretty small. It's only 4 miles across. And in this map, they're plotting the amplification, how strong the shaking is getting at each location, as the size of this circle. And I want to draw your attention to these 2 circles here. These 2 circles are about half a mile apart. They sit on the same stuff. If you were to dig a shallow hole beneath each of these locations, you would find the same sort of stuff, some sort of sand. However, this circle on the right is much, much bigger than the circle on the left. In fact, it is 3 times bigger. Half a mile away, you're getting 3 times stronger ground shaking. So what was the culprit here? Seismology is a bit of a detective endeavor, much like Ashley's work. And the scientists doing this work, they discovered that there was an underground feature that managed to focus earthquake energy right on this location out here. Half a mile away from this one, making a huge difference. But we cannot dig everywhere. We don't know what's down there in every single location. And our Earth is complex. However, you want me to be able to tell you how strong the shaking will be where you live or work. So we've got a problem here. So us seismologists like to work with incomplete data. So we produce things called ground motion models, ground shaking models, our best guess for earthquake shaking. So these ground motion models are pretty important. If I showed you one, you would probably be panicked by the complexity of it. But they are used to answer questions like, how strong should I build a building for it to survive for the next 100 years? In this map, we have the chance of damaging earthquake shaking for the next 100 years. And yes, you guessed it, California is all red. Virtual certainty of getting damaging ground shaking. In the early warning space, we use a ground motion model to say which regions should get alerted in the next big earthquake. And ideally, we want our ground motion models to be able to tell us, we give it our location, and it gives us a very specific answer about the ground shaking in that location. However, up to now, we haven't had the data to do that. The models give us a generic answer. So can we do better? The answer is yes. So with this money that we've been investing in our early warning system, we've grown the network, the seismic stations that exist in the States. This animation is playing along. It will show you how the network across the US coast is growing, and it has grown in the past 10 years 4-fold. So we have 4 times as many seismic stations now as we had in 2015. And we've reached a point where we have data every 5 to 10 kilometers. If my math is working out right, that's about 3 to 6 miles. So that's a lot of data. We can do a lot with that. So we can build location-specific models that can make use of all this data, but they also do a lot better. They fit the data 30% better. So with these new models, what can we achieve? Here is a bit of a complicated plot, but I chose to show you this because it really shows you how much difference a lot of data can make. So this is for a location in San Jose. It's the chance of getting ground shaking over time. This y-axis here is showing you the chance of exceeding the shaking level shown on the x-axis every year. So going down this axis, the shaking gets rarer and rarer. Two curves are shown on this plot. The old model using generic data for everywhere, and the new model in gold showing us the answer for this specific location in San Jose. So let's compare these two models for a 10,000 year return period, shaking that we expect to happen once every 10,000 years on average. That's a 1% chance in 100 years. And we see that the new model is actually a lot lower than the old. It's 75% lower. So if I gave that number to a civil engineer, they would panic. They would say, I need to rewrite my manuals right now. New models, of course, cause swings in both directions, but the bottom line is that they change the way we do hazard calculations by law. But we can't do this everywhere. We don't have the data to do this at the detail we want to be doing it at. So is there anything else that can help? So yes, you guessed it. The humble smartphone. So smartphones can record ground shaking everywhere. So every time my shake pings your phone and starts screaming at you, drop, cover, hold on, earthquake, it sends my database a waveform. It sends a wiggle. A wiggle to the seismologist is power. It is information. And when we get lots of these waveforms, we can build a data set of thousands for where the people live. The Bay Area, Los Angeles. And surely, these smartphones can give us detail about the shaking as it is happening where we live. However, one last problem. Smartphones are in buildings. Smartphone waveforms are recorded in buildings, not at ground level where we like to put our seismometers. The buildings will tend to change what the seismometers are picking up. So here's a plot from Sarina Patel, a former Science Envoy from 2023. She checked the data for an earthquake in LA, and she's plotting here on the y-axis the strength of shaking from the waveform against distance on the x-axis. The green shows you the smartphone data. The orange shows you the traditional seismic sensor data. And there's clearly a big offset between the two data sets. Sarina worked out that this difference is about 3 times. Smartphones record 3 times stronger shaking inside the buildings compared to traditional sensors. So we cannot just plug and play the smartphone data into what people are doing right now. So for my PhD, I've been trying to develop ways to analyze the data, the smartphone data, uniquely, to keep it within its own comfort zone. So let's try and see what we can do with this smartphone data. So this is a map of the LA basin. I picked up a satellite image, and we're plotting a magnitude 4.5 earthquake in 2020. Shown this location shown by the star. They might be a little bit small, but there are some triangles plotted here that shows you seismic stations that recorded shaking from this earthquake. And we color the triangles by whether they are above what we would predict for an earthquake of this size, or below. Blue is below, red is above. So you can get a pretty good picture of what's going on, like red in the San Fernando Valley, a little bit of blue downtown LA, but there are lots of gaps on this map. You couldn't guess what is happening here, for example, because we have no data. So let's go and add the smartphone data. Much better. So we have a lot of data density. Where we didn't have data, we have data now. But what really excited me when I saw this plot is that you can make out way more detailed patterns using the smartphones. And most importantly, where you see a red triangle, the standard sensor is above the model, we see red circle. And where we see blue triangle, standard sensor is below the model, we see blue circle. So the two data sets agree. They're telling us the same story. And we worked out that the strength of the information from the smartphone is about 40%. 40% of the way to what you would get by having lots of expensive sensors all across the area. So eventually we can get to a point where we know the answer to our ground motion problem on a block by block basis, where you live. So now what? We're working to find more ways to use our smartphone data. What parts of our signals influence the way that you perceive shaking? What parts of our signals are due to the buildings versus due to true ground shaking? So these are all questions that make me very excited as a scientist. But I cannot do this without your help. MyShake is a citizen science app. It relies on its users to get the data. So how can you help us? Download the app and keep it running. If you do that, you will get earthquake spoilers, earthquake early warning, and you will give us the data that we need to give you more information that will keep you safe. So, to summarize, I've shown you that the strength of earthquakes really matters for designing buildings, and it varies a lot in space. Smartphones can record earthquake shaking everywhere, where the people are, and that smartphone records can really help us in predicting ground shaking in future earthquakes. So, don't forget to download the app, and that's what I have for you today. Thank you very much. All right, questions? Yes?
So in the past, my wife and I have used USGS maps that predict shaking data to decide where to buy a house. And I'm wondering how that might correlate with this, because this is definitely done after that's been done. That's sort of older data.
That's
Or
right.
we looked at that or found correlations.
That's right. So the map you're referring to is a seismic hazard model. So it really tells you where the shaking will be stronger over a long period of time, you average over time. We haven't tried to do seismic hazard calculations using the MyShake data. We are at a very early stage in this research. We do believe that there is a way that we haven't figured out yet to marry the two data sets and exploit both of their strengths while mitigating their weaknesses. So taking advantage of the quality in the seismic sensor data while taking advantage at the same time of the very large spatial sampling of the MyShake data, the smartphone data. Yes?
How can MyShake tell the difference between an earthquake and me having a great time on the dance floor?
That is a great question. So that was a fundamental problem that was foreseen by the person who developed MyShake, Chin-Kai Kong, 10 years ago. So 10 years ago, the words machine learning were probably not in everybody's daily vocabulary. So Chin-Kai was a pioneer in that respect. He developed a machine learning-based algorithm that can distinguish between human activity and earthquake activity. Now that algorithm is now 10 years old, and we're actively working to make it better. So for compiling this data on this, in this talk, there was a lot of manual seismologist input of me looking at wiggles and deciding dance or earthquake.
Savvas, you told us that you've come 7,000 miles, first from Cyprus.
Mm-hmm.
I think of the Mediterranean as being volcanically active. Is it not seismically active earthquake-wise?
It is. So people might remember in our corner of the Mediterranean, the Eastern Mediterranean, where I come from, in 2023, in February, the Turkey earthquakes. So the Turkey earthquakes caused a lot of damage down in the southeast part of Turkey, in the Bay of Iskenderun, as it's called. A lot of ports were devastated. And we do know that that is not the end of the seismic risk in that part of the Mediterranean. Greece has had a history of large earthquakes. Large earthquakes have been documented to have caused damage to the great civilizations of the area, like the Minoan civilization. In Israel, they're really worried about the Dead Sea Fault, which is a fault that runs the entire length of the country. There's faults that straddle the entirety of the country of Turkey, in Greece, in Italy as well. If you go to the other end of the Mediterranean, to Portugal, you jump into the Atlantic. 1755 was really the earthquake that jump-started the study of earthquakes. The 1755 Lisbon earthquake, it really devastated the Portuguese monarchy at the time, and it created a big tsunami that made people very aware of the dangers of earthquakes and tsunamis in their backyard. So yeah, the Mediterranean is very seismically active. Not as active as California, for sure. For sure. California is really very, very active. Any more questions? Yes?
Is the intensity recorded on the smartphone affected by how high someone is in the building?
That is a great question. So the gentleman at the back is asking if the intensity recorded by a smartphone inside a building is affected by where you are in that building. So that's a great question. We do know for a fact that buildings, when you put ground shaking into them, they will kind of vibrate in this way. You might find YouTube videos from the 2011 Japan earthquake where you will see the tall buildings in Tokyo just wiggling like twigs in the wind. And it is a fact that you put the ground shaking in the base of the building, the top of the building will tend to sway a little bit more compared to the base. So there are beautiful examples where people have instrumented, I would say, at great cost, buildings both in California, in Asia, and in Europe, where they put sensors at every floor, and you do see the shaking that is experienced by those instruments getting amplified as you go up the building. But I will mention that we have a very exciting effort right now using MyShake phones to do that at zero cost. Yes?
I just want to make sure I understand, and it's related to the previous question. So you have the expensive sensors versus the app, and you showed there's an offset in the data there.
Mm-hmm.
And then I think what you showed after that was that even though there's an offset, that basically they kind of trend in the same direction,
Mm-hmm.
but you didn't manage to solve the offset. Is that correct?
That's true. So we want to live with the offset. We embrace the offset. So what we did, instead of plugging the smartphone data into the same sort of models that predict ground shaking for ground level, and those models are derived from traditional seismic station data, we went and derived a new model that incorporates the offset and is tailor-made for smartphone data.
It's dangerous.
Exactly.
A fudge factor.
It's not a fudge factor.
No.
It's a model that captures the behavior in the smartphone data. And it's two independent data sets
Yeah.
that once you treat properly, they're telling you the same story.
Do you think that offset was because people are in tall buildings?
Yeah, definitely. So I'm not a civil engineer, so I can't exactly speak to the mechanisms that offset is created, but we have collaborated with some civil engineers who've told us, yeah, that scale factor of 3 is about the right scale factor that you should be seeing because we built it. So, do you have time for more?
Yes.
Yeah. So, question at the very back.
So are you basically just dividing it all by 3?
So the question is, are we basically dividing it all by 3? The answer is no. We are deriving scaling relationships that go from basic information we have about the earthquake, the magnitude, how far away you are, and predicting how strong the shaking will be for the smartphone. And there are existing relationships that predict what the strength of shaking will be for the conventional sensor. So by having tailor-made models for these two data sets that we acknowledge are very different, we're able to capture the fundamental differences that they have and then compare them on an equal footing. A question by the gentleman in the purple t-shirt.
So it's recording the shakings as it's happening, but is there any pre-warning you can give for an earthquake? Like, I notice they have the systems now, like maybe 4 minutes is the max, but you can get a...
Absolutely. So you might remember that I talked about earthquake early warning at the beginning. So the earthquake early warning system we have here in California is called Shake Alert. It is run by the US Geological Survey. And what it basically does, it has the network of sensors that I showed, those 1,500 sensors that we have all across the West Coast. They are continuously listening out for earthquakes. They're able to detect the earthquakes when they start, and they are able to rapidly determine where they are, how big they are, and then we're able to give you a few seconds of warning. MyShake plays a central part to that because it takes the warning from Shake Alert and delivers it to your phone. So we're able to give you a few seconds. In the worst of cases, the warnings might come after you feel shaking, but in the best case scenarios, if you imagine an earthquake up in the Pacific Northwest, in Cascadia, you might get up to a minute of warning before you feel shaking.
How long?
A minute, a whole minute. Question by the lady.
I'm wondering about when we build housing, is it better to have a building that is more flexible, or with like a 3D printer where it's kind of printed house, it's all one, it kind of floats?
So that's a great question. I'm not sure about 3D printed buildings and their seismic resilience, but I can say for sure that much of the principle that earthquake-proof design is based on making buildings flexible, making buildings that can go with the flow. So we know that in a lot of regions where there were traditional dwellings built out of wood is known to be a very flexible material. Those buildings cannot collapse because wood is very flexible. So if you think about probably a lot of the houses that people in this room live in, they're made out of wood. So they are very, very flexible and able to withstand pretty strong shaking. Yes?
What about very, 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 very tall buildings?
That is a great question as well. So you might be thinking about the San Francisco skyline, a lot of tall buildings in San Francisco. So tall buildings are a different beast. Tall buildings are not just a simple stick that shakes in the wind. They're very complex. Architects like to make them into intricate shapes, and I can't say this as the son of an architect. Engineers hate architects when they make complex designs because they are hard to make to stand up. So tall buildings require a lot of work to do their seismic engineering. So I will take your question and twist it a little bit. For example, the Chase Center in San Francisco, where the Warriors play. The site of the Chase Center is built on old rubble. So it's not a great site to build on. But the owners of the building were told that by their engineers, and they actually put in a lot of money to make sure that they did all the studies that were required to make sure that their building can withstand very high levels of shaking that would be possible because their site is on such perilous ground. So you can't build on the worst kind of ground. You just need to spend a lot of money.
Abu Dhabi, isn't it Abu Dhabi where they're building the tallest in the world or something extremely,
So,
isn't it?
I'm not really sure about the details here. I think the tallest building in the world is in Abu Dhabi.
It looks really, I think it's Abu Dhabi.
Yeah, and I will say that, to your point, I'm not an engineer, I'm a scientist. I just give the engineers the information they want from me, and they can do whatever they want with that information. The task of the engineer is to build as strong as they can for the lowest possible cost. So an engineer, when they're building a building, they're not only considering the earthquake problem, they're considering wind, they're considering flooding, they're considering all sorts of things. So I have huge respect for engineers who have to balance all these problems, but as seismologists, I think we will make them love us more if we give them more information, and information that has less uncertainty about it. Engineers hate uncertainty. They like to be certain about things.
Marco, just one more, please. One
Yeah,
more.
of course. The gentleman in the green shirt.
It seems like cell phones have disadvantages and advantages. Disadvantages, even outside a building, it's not sitting on the ground. It's in someone's hand or in someone's pocket. But bigger earthquakes also shake for a longer period of time, which a phone would be very good at measuring. Can you speak to those advantages and disadvantages compared to your professional seismometers?
Absolutely. So that's a great question. So the question was, what are the disadvantages and advantages of smartphones with respect to conventional sensors? And the gentleman was asking about large earthquakes where the shaking gets to very high levels and lasts very long. So to preface my answer to that question, yes, large earthquakes will shake much more strongly and will shake for longer. And it is true that smartphone accelerometers, the types of sensors that record vibrations in smartphones, are nowhere near the quality of the expensive, tailor-made instruments that we put out in the field that require an engineer to go and install them. Smartphones, if you put them one-on-one, if you ask me as a seismologist, would I want to install a smartphone or a traditional sensor, given the option, I would install a traditional sensor any day of the week. However, we do not have the money to install the traditional sensors everywhere. And the benefit of the smartphones, they're not as high quality sensors as a unit. But if you get lots of those observations, and you have observations telling you the same story, if you put them together and aggregate them and average them, then that's very preferable to having no data. So my approach to this problem is quite simple. I do not discard any data. Any data is good for me. For the seismologist, For such a data-starved field, any data is gold for us. It's power, it's knowledge.
Thank you, Mark.
Thank you very much.
Previous experiences with Science Envoys have taught me that you, the audience, like to hear a little bit about these great PhD students. So I'm going to ask Ashley to turn her mic back on, and Savvas, please stand back up, and let's see if they'll answer this question. What was it in your science upbringing that got you excited about your respective fields, that allowed you to fall in love, maybe? Dopamine, sorry.
Okay, I'll go first. Can you hear me?
Yep.
Hello? Okay. So I think that this is probably a twofold answer. The first one is how I fell in love with science. It was in the first grade. I did this science experiment with my mom for a science fair, and I was enamored. So you take celery stalks, you put them in cups of dyed water, right? So we've got blue, we've got red, we've got orange. And I could see it in my kitchen right now. You put the celery in those cups, magic happens. The water moves through the stalks through a process called translocation, xylem, phloem, all these really cool things happening inside the celery stalk. And then I come back, I wake up in the morning, and I can see a blue stalk of celery. It was then that I fell in love with science, because I really liked how you could sort of explain the craziness of the world, or explain these sort of intricacies through detailed, structured processes. I liked that control, I liked that rigor. And then growing up, I became more and more fascinated with how this black box of a brain leads to the way we interact with one another, and the way we interact with our environment. And then I found out about neuroscience, which is exactly the study of this black box and how we interact with our environment and everybody else. And I'm hooked. Turn on.
So similar to Ashley, I think it's a twofold answer once again. I did make a lot of jokes about engineers in my talk, but my grandpa was a civil engineer, and he really loved telling you how things worked. So I was a little child spending time with my grandpa. I remember he must have told me a lot about how boilers work, because I would go to school in first grade and tell my teachers how boilers worked, and I thought that was a little bit weird. But I think that was the bug. The bug was seeded at that point. I think I grew a great love for the way that things work, and then I carried that through all the way until high school. Back where I'm from, earth sciences are not really popular, but I was very lucky to be able to take physics and geography classes at the same time. And then that was when the light bulb went on, the link clicked that you can use pure physical science to describe these big forces that the Earth produces. Earthquakes and volcanoes. Earthquakes, the biggest earthquake that we know is 1,000 kilometers long. That's 600 miles from here to LA. So that's big. And the thought of these big things that exist on Earth and that we can use pretty simple physical principles to explain them was what got me hooked. So I think I was no turning back after that. I went into earth science, geophysics, seismology, and here I am, 7,000 miles away.
Thank you for being here this evening. A final round of applause for Ashley Moses and Savvas Marcou.